You should know that, but it's not in the quiz. All right. So that's the plan. So now, where are we here? Main idea on the stuff we've done is we are at algorithms. Algorithms have a runtime, and very often this runtime it's a recurrence. Right? So I want to think in this way. The reason this is often a recurrence is because computer science and computer scientists solve problems by what's called divide and conquer approach. Divide and conquer. Solve smaller problems and combine results. Right? This is more like a philosophy. It's not an actual algorithm. But if that's my approach to do, say, sorting, or to do traversal in a graph, or to do whatever, very often I'm going to end up with the recurrence. Because by solving smaller problems and then trying to put the result together, it means, think about Mergesort, right? What's the runtime of Mergesort? We'll have to split in half, sort the halves, and then combine, right? It's kind of a divide and conquer idea. Because of this, splitting in half takes nothing. Sort the halves is 2 halves times t of n by 2. If this whole thing is t of n, sorting a half will take t of n by 2, and combine is a linear time, right? By the way, be careful here. I'm pretty sure the quiz contains problems of to get you confused between insertion sort and selection sort and merge sort and whatever other sorting is. So make sure, I know it's an easy thing, make sure by tomorrow the quiz you know exactly which one is selection sort, merge sort, insertion sort, and exactly what the steps are in those things. So in here, the recurrence is going to be, well, I need to do 2t of n by 2 plus n. It's really theta of n, because this is not, maybe it's a constant times n, but I'm going to say it's plus n to simplify things, right? In binary search, my time is really what? Split in half, right? And then compare, and then recurse on one of the halves. Search one of the halves. So what is it? Split in half is nothing, compare is nothing, and this is t of n by 2, right? Because I'm going to that one half. Everybody remembers binary search? I'm checking the middle, it's already sorted the array, and I'm deciding, once I check the middle, here's the middle, here's check the middle, and then say, do I have to check left now or the right side? Either way I go, it's n by 2. That's why I pick the middle, so I can't get unlucky in binary search. If I pick something that's too high or too low, and I'm unlucky, I'm forced to search the bigger part. But because it's in the middle, whichever, unless I'm very lucky and I found the value at the comparison, I will have to do half of it, right? So in here we get t of n is t of n by 2 plus 1. This is not exactly accurate. I should say theta of 1, because really a constant there. This would be theta of n. It's a constant times n. Maybe this combination takes 2 linear steps, like 2n or 3n. But for simplification, I'm just going to go by this way. So I think we've done a bunch of these. And I think maybe I'll take 5 minutes now to recap some other algorithms we did for graphs. Because I think your homework and recitation paper might contain something with graphs. The main problem we need to solve to move on from algorithms and all that is how do you solve this stuff? Once you get to the pure math, forget about the whole problem, computers, all that. Once I'm here, I want to know how big this function is, asymptotically speaking. I'm very rarely going to say I want the exact t. Well, we did an exact one. Let me put it here, Fibonacci. We didn't actually, I think we motivated some computer science problems with it. Remember there was one with how many string of 8 bits don't contain consecutive ones? Remember that one? No consecutive one? One bits in a string. So there are some applications, but we work on that one by giving the formula direct, which was f of n plus 1 is f of n plus f of n minus 1. Usually for recurrences, we don't specify the base. We don't say who is t of 0 or t of 1. But sometimes we do. To have it an exact function, this is not perfectly determined unless I specify the base cases. For Fibonacci, what did we have? F0 was, or was it F1? Was it 1? And F2 was also 1? Something like that? I forgot. You can start the same recurrence now with 1 and 1. You can start at 3 and 4 if you like. So the recurrence is the same, but the actual function values would be different if I change the base. So sometimes in early classes like this one, somebody might ask, if I give you this recurrence, what is f of 5? So you go ahead and compute, add them up, and you get to f of 5 that way, right? But in general, the computer science problem is more like, I don't specify the base, I want the asymptotic growth of this function. Is it like linear, quadratic, n log n? Is it like exponential? What is it? That's the actual computer science problem. Without specifying the base, what is the growth? Asymptotic. Ideally, we mean theta of something, because theta is the best bound we can have, right? Is the one that's within the constants of that function. But if not, okay to have an O bound and an omega bound. Right? This one, theta is the best, is saying this function is like n squared within constants. If I can't be exact, I'm going to say, well, it's bigger than n, it's bigger than linear, and less than n cubed, but I can't tell exact what is it in there. So ideally, we like the theta bound because that's exact. If we can't get it, we accept the other ones. Say at least it's bigger than that and smaller than that. Right. So we actually did this one, right? Didn't we spend almost a lecture figuring out the Fibonacci whole thing? We have a closed formula for Fibonacci, right? The 1 plus square root of 5 by 2. But what was the moral of this? I think we proved that f of n is exact phi of n, right? Where phi was 1 plus, what was it? 1 plus square root of 5 by 2, is that right? Or not? I forgot. Anybody can figure out what's this is called the golden ratio. In any case,
yeah.
What kind of function is this? Exponential function with this base. So I know the exact theta bound. It's an exponential on this base. It's not 2 to the n, or 3 to the n, or 1.1 to the n. It's this golden ratio to the n. That is the Fibonacci asymptotic growth. So we solved this one. I show you guys how to do it. I think in there I showed you a little bit of an intuition. Say my intuition was if this is exponential, that was a guess, right? I guessed it. I think just like exponential. Then the exponential has to have the property phi at n plus 1 is phi at n plus phi at n minus 1. That is like taking things to a limit. I said if this is an exponential phi to the n, I don't know the phi, but there's some phi to the n, and this function is asymptotically growing like that, then to have this happening all the way to infinity, that phi at this power is that plus that, and solving this equation, which is easy, it's a quadratic equation, once you reduce the big powers, I got that phi. So that was one way to solve these things. Can I solve this one the same way? Guess it, plug it in, and see what happens? Actually, if you guess it, we plug it in, we found phi, but then we did prove by induction that that phi works out, right? Like if fn and fn minus 1 are the correct values, then the next one will also be the correct value. So guessing it and checking it is not quite complete. We did induction proofs here. If you go back to that lecture, we show not just the guess and the solving it, but rather how it's guaranteed to work. What if I do this one or this one? Can I do the same? Guess it, check it, and prove by induction, for example? Or in general, how do I solve these kind of problems that are usually coming from an algorithm that does some things, solves some problems, puts it back together, then I get a runtime. That is the main subject of today. How do we solve this stuff? And I'm going to start by cheating. It's a very good cheat, this one. Actually, it's an amazing cheat for this class. It's not that useful later, because later everybody knows it. So you can't really cheat. I'm going to give you a trick. That's a trick for now. That solves this immediately. Unfortunately, you can't use it formally, that trick. So you can check it to get the answers to those things, but you can't use it when you write your paper. Now, if you don't want to do that, you don't have to use my trick. But with this trick, you get an answer very fast, and it's much more verifiable, and you get the confidence, as opposed to the grinding that I'm going to show you later. Go through all the steps. You're never going to know if you're right or wrong, because you can mess up the calculations. So I'm going to start with the result. That's called master theorem. Which you're not supposed to know and use, okay? So I'm serious. You cannot write this in your quiz or exams. If you do, you're going to lose points. It's actually specified that you're not supposed to use it. It's not like ambiguous, like maybe we don't teach you, maybe you can figure it out. Like we said before, there's some theorem that somebody was saying from coloring, can I use it? Okay, fine. This one is absolutely forbidden. But it will be great to use it first just to get an answer to see where you need to go with those recurrences. All right. So master theorem for recurrences says something like my function is something like, I'm going to give there's many versions of this theorem. The one that I'm going to give is something like a dn by b plus n to the c, where a, b, c are numbers, positive, those are constants. So if you notice, this one fits in that form, does it? Who's a in here? 2. Who's b? 2. Who's c? How about this one? Who's a? 1. Who's b? 2. Who's c? 0. See? Most of this stuff, in fact, all the recurrences in all those notes, in all the classes in the previous years, and all the exams and all the quizzes fit in that theorem. Ain't that great? That will change when you take algorithms. There are some recurrences that do not fit that. How about t of n equal to t of n minus 2 plus n by 3? Does that fit? No. How about this one? Does this one fit in there? Is there an A, B, C that gives me Fibonacci recurrence? No. So it's not to say all the recurrences fit in there. No. But a lot of, all the recurrences that you guys are going to have to solve from now to the end of the term going to fit in there. So it'd be a good way to just check the answer to see what you need to get.
So we said binary search fits in there, but also that C is supposed to be greater than 0.
I think C can be 0.
Okay.
Good observation. So, here's the magic with this theorem. There are 3 cases. It comes down to how is C versus log in base B of A. So there are, of course, 3 cases. Case 1, let's say, when C is smaller than log base B of A, in that case, the recurrence will come as theta of n log base B of A. Case 2, when C is log base B of A, then T of n will come as theta of n log base B of A times log of n. In case 3, C is bigger than log base B of A, in which case this is going to be n to the C. The answer, as in the whole recurrence, this is saying this is going to grow like this function, this is going to grow like this function. Notice that this and this are not the same growth. This function is the same times a logarithm. That's now within constants. So this is not the same theta. It's close because this function can be n at a very big power, could be n at 5th. N to the 5th and n to the 5th times log n, they're different growth. This one grows a little faster because it has the logarithm in it. Right. So, do you trust me, believe me, or do you want a proof? I mean, we don't have to do a proof. The proof is in the notes, in my algorithms notes, that is. It's not complicated. We can attempt to at least an idea of a proof. But since you can't use it anyway, this is good if you can remember or write it down. It'll be amazingly fast to check up the results on an exercise, to know what you're supposed to get. And then you still have to grinding, all the steps. So let's apply it here. What happens here? A is 2, B is 2, C is 1. What case is that one? Which case has the property that log, how much is log base B of A? Log base B of A is log base 2 of 2, 1. And C is 1. So which case it's that one? It's this case, right? It's case 2 because log base B of A is 1, which is the same as C. So because it's case 2, what's the answer? Theta of n log n. How about in here? What case is this? A is 1, B is 2, C is how much? 0. So how much is log base B of A? 0. So what do we have? Log base B of A is 0, which is the same as C, right? So what case is that one? It's 2 again. So the answer is How much is n at log base b of a? This is n at 0, right? So that's 1. So just log n. How about I'm going to pick one at random that's in the notes here. Let's see. Here's another one. T of n is 4t n by 2 plus n. This is one from the notes. I pick it at random. What is a? 4. What is b? What is c? 1. Log base b of a is log base 2 of 4. It's how much? 2. How is this compared to the c? It's greater than 1, which is c. So what case I have? This case here? Case 1. So d of n will be theta of n at what power? 2. Easy, right? Hands up, who's with me? Good. If you remember this theorem, I suggest remember it exact. Because the fun part is I'm applying that theorem, I'm so smart, I get the wrong case, 0 points, right? Like, if you you have two options. Either ignore, says, you know what, since master theorem is not allowed, I'm not going to pay attention to it. I'm going to get to it in my algorithms class 2 years from now when we learn it there. That's totally acceptable for me. The other option is to say, that's a good trick. I could solve problems in my head without even writing down. I'll know the answer before the others are trying to see what it is. I already know the answer, that's great. Then remember it exact, so you don't get lost. Now, since we can't actually use this, it's good to know where we get, but what else can we do to solve this other than master theorem? So we can't use master theorem, but we get the answers. Answers are useful, right? I know what I'm supposed to do with my proof or with my induction proof or whatever I'm doing. So how I'm going to solve some of these problems? Let's see. Let's take some recurrences and try to solve them. One recurrence in here. How about this binary search one is the easiest one. T of n is T of n by 2 plus 1. Again, I'm ignoring the base because the asymptotic growth is not depending on what the base is. Whether T of 1 is 1 or T of 1 is 3 or T of 1 is 100, I get the same asymptotic rate or growth of this function. And I don't care about the exact values unless the problem says give me exact T of 17. I care about which order of growth am I going to get. So my favorite method other than master theorem, or when master theorem does not apply, like I said, there are some recurrences for which master theorem does not apply, is to try it out a few times just to see if I can guess a pattern. So that's called the substitution method. Okay, so T of n is 2 T of n by 2 plus 1. Substitution method says repeatedly apply the recurrence initially to T of n, but now I can apply the recurrence here, right? I can apply the same exact formula, but now for n, instead I apply it for this, because that has to be true for any n, right? So what happens if I apply the recurrence? What's the result of applying this formula for n by 2? What do I get? T of, what happens in here if I put n by 2? T of n by 2 is who? T of
4 plus 1.
Right? It's a little bit like in integrals when you do a change of variable, only that you don't have the dx factor here. So I'm putting n by 2 instead of n, and I get, of course, n by 4 on the other side, because that's n by 2 by 2. This n by 4 is really n by 2 by 2 plus 1. So I can apply that in here and get n by 4 plus 1. that's just this guy. I still have a plus 1 from here, right? So how much is this? T of n by 4 plus 2, right? What happens if I apply it again? I'm applying now the same formula for T of n by 4. I get T of n by 8 plus 1. That's this thing. I still have a plus 2. So I get the T of n by 8 plus 3. What happens if I again apply this recurrence formula? I get T of n by what? What?
16.
16 plus 1. And I still have the plus 3. So that's going to be T of n by 16 plus 4. So at some point, I could do as many steps as I want here. I have to figure out there is a pattern here. In other words, okay, if I'm going to do this k times, I keep this is like 1 step, 2, look at the first step, second step, third step, fourth step. This was k equal 4. In general, after k steps, can I tell what the form will look? That's just guessing. They look at these formulas and say, if this is after this is the first step, second step, third step, fourth step, can anybody make a guess what's going to happen after k steps for any k? How is this going to look? This one here. It's going to be what? Yes.
T.
Yes. Hold on, give him a chance.
It'll be n divided by 2 to the k, and then plus k.
Plus k. Is that it? Guessing a pattern is saying, well, I always notice that for each step I move on, I divide by 2. And this additional term, for every step I move on, I increase by 1. So here's a piece of good news. In this class, as far as the regular curriculum and exams go, a guess that's correct, it's good to go. As in the algorithms class, you're not just doing the guess. You have to guess it here, but you have to prove it. In this class, if you guess it and you are right, that's full credit. We don't require the proof. At least not the regular section. We don't require the proof. It'd be nice to know how to make the proofs. We'll do one in a second. But guessing it correct, the last piece after you guess it correct, if we believe this is the case after k steps, is when does it end? Where is the last k? So if this is after any k steps, k could be 20, 25, 30, 50, 100. Actually, what is the last k? When does this whole thing end? How do I think about that? Because if I'm to write it manually, from say n equal 100, I'm going to keep down and down and down. At what point do I stop? Yes.
Log base 2 then, because then you'll have T of 1.
Right. So I don't want you to think from the log base 2 of n. I want you to think, what do I need inside this parenthesis to stop? So the end is the T of whatever is inside. The inside part has to be about 0 or about 1, or about some small constant. So depending if you're doing subtractions or divisions or whatever, there's a shrinking mode for this, right? The more you go down, the more this is going to go down. And if you divide repeatedly, you want to get to 1. If you subtract repeatedly, you want to get to 0. So in here, the inside, to make that 1, we need n by 2 to the k to be approximately 1, right? The inside part of this formula has to be about 1, which means, like he correctly pointed out, k has to be about, what k do I need such that n divided by 2 to the k is 1? Log base 2, all that. So there's three parts in here. Doing the patterns so you can see this with your eyes. Number two, guessing a general pattern that is not after 2 or 3 steps, but after any number of steps. And the last part is, when does it end? At what point the inside here becomes small enough to be the base case, T of 0 or T of 1. So now that I do this, I'm like, okay, well, I'm gonna write directly the last one. If I really put k equal log base 2 to the n in the formula, I get T of n equal T of n divided by 2 add log base 2 to the n, right? Of course, I put that k specifically to get T of 1 inside there. So no surprise, it's going to be T of 1. Plus this free term will be log base 2 to the n. That is T of 1. 2 log base 2 of n is n divided by n is 1. That's why I got the log base 2 of n, to make sure this is a 1 inside, plus log base 2 to the n. This is theta of log base 2 to the n. For logarithms, you can just say log because all logarithms have the same theta. It's just a matter of constants between them. Whether it's log 10 or log 2 or log 3, it doesn't really matter as an asymptotic notation, because all logarithms are within constants of each other. Yeah? So that's that. Again, for this class right here, this method will give you full credit. Write a few steps, guess the pattern, general pattern. I'm going to say here, general pattern. K times K steps. Pattern after K steps, recursive steps. So now, what's not required and what the regular section doesn't do, suppose I'm in the algorithms class. I need to make an induction proof. I need to say, look, I guessed it, I think it's that one. In fact, didn't I already do the master theorem for this one? I did, so I already know from master theorem that that's correct. You know, that's the great advantage of master theorem, that you have a way to verify your answer immediately, or you have a way to know where these summations arithmetic is supposed to go. How do I prove by inductions? That T of n is this, right? That's what I've got. What this really means, I'm going to use the definition of theta now. What I'm really saying is T of n is between C1 times log of n and C2 times log of n. So that's what really theta means. It's within constants of log n. C1 and C2 have to be positive. And this could be any constant. Anybody can choose their constants. There's no restrictions what constants you choose, but you got to make sure you only choose them once. Like if you choose a constant, you got to stick with it. So how is the induction proof going to look like? So there's actually two proofs in here, right? Let's say I want to prove T of n is smaller than C1 log n for any n bigger than some n0. Remember, this order of growth needed to happen, but not for small n necessarily. It was okay to happen starting at some n0 start. Again, you can choose that n0. You can say it starts happening from n0 equal 300,000. That's fine. So I need a base case. I'm going to let you figure out the base case. But what am I going to do for the induction step? What's my induction step here? What am I actually going to prove? Remember, induction step, we have a premise and a conclusion. So what is the premise and what's the conclusion of the induction step? There's an implication in between them. So given what I want to prove here, how is this proof going to go? I want to prove that this is happening. I can pick the constant, and I can pick the starting point. I could say this starts at n equal 100 or 200, whatever, it's up to me. But then I want to prove that for any n starting at that point, this is true. So what is the premise and what's the thing? Yes?
T of n is less than C1 with bit log of n.
Is that the premise or the conclusion?
It's the premise.
That's right here. T of n is smaller than C1 log of n, right? That's the premise. Then what?
That implies that T of n plus 1 is equal to C1 times log of n.
That will be from n to n plus 1. Now, this is a valid wish, valid desire somebody can have. If you prove this, you're done, right? Problem is, I won't be able to prove this one. Again, if we prove this, that will complete the proof that together with the base case that T of n it's always smaller than that. But given the way this recurrence works right here, I'm not going to be able to prove that step. Yes?
Or we could do it with
2n, or let's actually do it like it's written here.
2n. Or
If T of n by 2 is smaller than log of n by 2, then T of n will be smaller than n. The reason I like this induction step is because this plays out nice with how recurrence works, this particular recurrence, right? If I can control T of 100, in order to state anything for T of 100, I'm going to relate to T of 50, right? Because remember, induction step, you have to relate the new customer with the old customer. From n plus 1 to n, I don't have a relation. I can't relate T of n plus 1 to T of n because I don't know how they're related. But I can relate T of n to T of n by 2 because I know they have this relationship. So now arithmetically, this proof is coming down to how this proof gonna go. T of n, I start with the new customer. Who's T of n? I use the formula, right? That's T of n by 2 plus 1. Now I use the induction hypothesis, right? I know for sure this is smaller than, because I use the induction hypothesis here. So what do I get? C1 log of n by 2 plus 1. And I need to show, I'm going to say here want, because I don't know this. This one I know, it's induction premise, I can use it as given. But from here, what I would like to get, this is smaller than what? C1, C log n plus 1. That's what I want, right? I'm going to do a bunch of derivations that go back and forth here. So if I get to true, I know I'm good. But I do on the based on desire here, not on the basis of what I know. This would be the same as saying I can reduce those two, right? And I can say now this is C1 log. How much is log of a fraction? Right, so this is C1 log n minus C1 log 2, right? Once I go away with 1, I'm going to write 1 because I don't know if this is true or not. This is C1 log n. Now I can reduce C1 log n with C1 log n, and I get 0 smaller than C1. How much is log 2? If I assume, let's just say I'm assuming log 2 everywhere. Log is log 2 to make it easier. Again, logs, you can choose whatever base you want because they all have the same asymptotic notation. So log base 2 of 2 is 1. Now this is still want. Can I now choose a constant to make it true?
Positive.
Remember, the constant is up to me. So I can pick whatever. I can say choose C1 equal 5, and that makes it true, and then it's reversible. Now, I think the other one might be a little trickier, this part that you say you need a C2 here, you know, like, you guys can try it out and see where you're getting with it. Now, I'm not insisting on these proofs because they're not required, but in your algorithms course, you're gonna have to do something like this. You're gonna have to say, well, I guessed it, I'm happy with the formula, I check with the master theorem or with some other mechanism, but how do we actually prove that my guess is correct? It's gonna be an induction proof. And I have some holes here. I only did one of the two, and I didn't put a base case. The base case might put some constraints on who C1 and C2 might be, because I need the base case T of 0, T of 1 to also satisfy those things, right? Yes?
If we're talking about asymptotic near infinity, why do we care about the base case?
Well, we need to prove it that it starts at some point. So it doesn't have to be T of 0 or T of 1. It could be T of your N0. You could say my N0 is 1700. Then, well, you have a base case at 1700, right? Because induction cannot be the only, induction step alone, it's only saying from here, you get to here, you get to here, you get to here. Now, to make all this stuff true, the initial ones must be true. Just by induction step, I can't get to all of them being true. But he's right. The base case may not be T of 0 and T of 1 because my N0 might be 1000 or whatever N0 I pick the starting point. So I can choose any fixed N0 and any constants as long as I can make it work from that. Okay, who's with me? Good. Let's do another one. How about the Mergesort? I have a nice master theorem in here. Again, remember you can't actually use the master theorem. You can't just say solution master theorem, that's 0 points. But you can use it on a scrap paper just to see what result you get, or you should get. So let's do this one. T of n is 2 T of n by 2, that's the Mergesort, plus n. I'm going to use the same sort of expansion. This expansion can be done in two ways, with substitution. That's my favorite. You can also do it with a tree. It's not really different. It's just the same concept, expanding, but instead of writing like this, I'm going to show you one of those, how it looks with substitution, and then how it looks with the tree. The concept is still expansion until the bottom, until it bottoms out, but just written in two different ways. So what do I get here? If that's step one. What happens if I apply the recurrence again? Who's T of n by 2? Plus n over 2, right? Think about it. If I apply the same recurrence, but not in the argument n, but rather the argument n by 2, I get 2t half of it, that's n by 4, plus it, which is in this case n by 2. If you think of the argument as an orange, this is 2 half an orange plus the orange. So if I apply for the n by 2 is the orange now, I get 2 half of that orange, which is n by 4, plus the orange, which was n by 2. Right? Plus I still have this n on the side, because that's coming from the top. So if I'm to write this nice, this is what? 4t of n by 4 plus, I'm going to say n plus n by 2. There is a little bit of magic in here. You'll be surprised perhaps how you organize this final step of the row before you move to the next expansion. It's critical in seeing the pattern. I know it's just little things like, okay, you reverse the n with the n by 2, and you do the 2 times 2 equal 4, right? Like, what if I don't do those steps? What if I leave it like this or something? I'm telling you, if you want to guess a pattern, like we guess in here, you know, it's critical. How do you write the last thing before you move on? Writing it in a proper form will give you easy guessing.
Doesn't the 2 distribute over to the n by 2?
Correct.
So,
N by n. 2 times n by 2 is an n, which is an n. So I could say here maybe 2n. How about writing it again? In here, I get the what? The 4 is the 4. When you expand, the first step in the expansion, try to put the whole thing in a parenthesis without doing other multiplications or additions so you can see clearly what you expanded. This is all about visuals because you're going to get down to a point where you have to guess. And guessing is going to depend how you look at it. How much is t of n by 4? 2t of n by 8 plus by 4. I still have a 2n from before. So now if I group the terms, I get 8 t of n by 8 plus 4 t n by 4s, that's n, plus 2n, that's 3n. One more time. This is going to be 8 expansion t 2t of n by 16, right? Plus this is going to be n by 8. I'm just expanding this thing in here. Plus the 3n from before. This is going to be 16t of n by 16 plus 4n. It's 3n from before plus 8 times n by 8. I get another n. Right? Can we guess it now? Can we make a guess? Dot, dot, dot. After k steps, general pattern. We get what? 2 to the k. Like that? Okay. That's the general pattern. Again, that's guessing. It's going to depend how you write this up. Depending of how you see this, how you write it, you know, if people write it, for example, 2 to the 4 t of n by 2 to the 4 plus 4n, it might be easier to guess, for example, right? In that shape, you can say, okay, that was 2 to the 4, this is 2 to the 3, this is 2 to the 2. How easy is to guess? It comes down to how much practice you have and how you look at that term in there. What is the last k? Where it ends. What k? This is the same pattern I had before, so it's going to be the last ending. I need to drive this part to roughly 2 to the 1, right? So I need n divided by 2k to be roughly 1, which means k has to be roughly log base 2 of n. So now by replacing, by substitute last k in pattern, I get t of n is, what happens if I substitute this k, the last k, inside here? I get 2 log base 2 to the n, t of n divided by 2 at log base 2 to the n. No surprise, this is going to be 1 because that's how I pick the k. So that inside the t is 1. Plus k is log base 2 to the n times n. So how much is all this? 2 add log base 2 to the n is n times t of 1. So let's write that down. T of 1 plus this in here is n log n, right? This is n log base 2 to the n. Now in terms of theta, if I have two functions, what is this function here? That's linear, right? Between two functions, it's only the bigger one that dictates the asymptotic growth. If one is bigger than the other, I can just keep the bigger one. We know that, right? So this is n log n. Because this is a linear function, that's n log n. N log n is bigger, therefore I get the asymptotic. Didn't we know from the master theorem that it's going to be n log n? Yes.
So we can always get rid of the one that's smaller. Why on the master theorem, but that's case 2? Do we actually include that as block of it?
In master theorem, we don't have an addition of two functions here.
It's multiplication.
Right? It's a multiplication here. But in the addition of a fixed number of functions, as in 2 functions, or 3, or 4, not in the infinite number of functions, or undetermined. When you know I'm adding 3 functions. Suppose I'm adding 2 to the n, plus n to the 100, plus n to, factorial. What is this? That's n factorial. Because I have 3 functions, I know exactly how many there are, and I know which one is bigger, as in always bigger, asymptotically. N factorial would be bigger than those 2 guys, so this whole thing is theta of n factorial. All right. Let's see what would happen here if I draw a tree. How do I think of this with a tree? So this exact problem. If I have the tree for this particular one. Oh, I have the tree for another one here. Let's do this one. And here's the same. In the algorithm class, we need a proof by induction. If we stick at guessing, and here's the answer, we're gonna need the proof by induction that says, so let me write that in there. I'm not going to do the proof, but I'm going to state what we need. So once we got to here, what do we need? T of n is theta of n log n, which means what? T of n is smaller than some constant times n log n, and bigger than some other constant times n log n. We need to prove that there is a constant and another constant, and there is an n0 such that for any n starting at n0, this happens. So n0, the starting point, and the 2 constants are up to you to choose, but you can only choose them once. And then we'll have to make this proof by induction. I mean, you can make it by any technique, but the induction is the technique that will do it. So let me again try to at least give you a hint of how this proof works, 1/2. Let's say I want to make this proof here. So I am taking this half. T of n smaller than C1 n log n. I need a base case. But other than that, what's the induction step going to be? Again, induction step in here, it's going to be dictated by how the recursion controls who depends on who. Right? So like before, I'm going to say if T of n by 2 is smaller than C1 n by 2 log of n by 2, right? I'm just replacing here n by 2. If I know this happens for n by 2, I'm going to try to prove it T of n smaller than C1 n log n. The reason I choose this induction step, which is a strong induction, because if n depending on n by 2 is not depending on n minus 1. I choose this induction step, again, because of the recurrence that's given to me. So how do I prove this? Like before, I start with a new customer, T of n. I know the formula, that's T of n by 2 plus n. I apply the induction hypothesis here. So this is smaller than 2 is a 2. I apply the induction hypothesis on T of n by 2, right? So I get C1 n by 2 log of n by 2 plus n. I have this term here. Is that right? T, 2 is T, this is C1 and 2, right? So this is the expansion of the induction premise for n by 2. And I got a plus n. So now, that's I know, but what I really want, I want 2 C1 n by 2 log of n by 2 plus n. I'm going to say one thing here, because I didn't prove this. I want it to be true. Smaller than what? The target. C1 and log n. Who's with me, what I'm doing here? Who's following me? So what am I doing? I'm saying I want to prove that this property, if it's true for the half, is true for the whole. And how do I do that? Well, I'm going to use the induction formula, induction premise here on 2 of n by 2. This is from the recurrence that was given to me. That's controlling how T of n relates to T of n by 2. So now what's going on here? I've got things like 2 times n by 2, that's n C1 log of n by 2 plus n. This is still in the want mode. C1 n log n. Can I divide by n the whole thing? If I divide by n, I get C1 log of n by 2 plus 1 smaller than C1 log by n. This is, I think, like before, isn't it? So this is, let me write this down as C1 log n minus log of 2, because that's the log of n by 2. So now I got C1 log of n minus C1. Log of 2 is 1 plus 1 smaller than C1 log of n. Now this whole thing goes away. So I need a C1. So this is all 1. 1, 1, 1. I can make this true if I choose C1 equal 5. Because 5 is bigger than 1. So now that I get to this point, I can reverse this reasoning. When I don't put anything between my equations, I really mean this can go back and forth. I don't put any implications. So once I get to something that's true, it means I can go back and get the original statement. Yes?
Since your induction step is saying that the statement of n over 2 implies statement of n is true, and the base case is n equals 1.
Base case doesn't have to be n equal 1. That has been asked before.
But doesn't it only imply, the statement being true for like power to 2? And not
Right.
every single n?
So I think that goes very well with the question that he asked before. What base cases do I need, right? Let's suppose my n0 is 50. What his point is, well, from 50, your induction takes you where?
100.
To 100, and from 100 takes you where? 200, and then 400, right? Well, how do I get to 101? Is something that implies 101? That's another thing that you're going to have to do in the algorithms. How does really work if n is 101? What is n by 2? What is n by 2 exact? It's 50.5, right? So this doesn't really work in an integer space with 50.5. So there will be something in the algorithm that says, you know, you can round that 50.5 to either up or down. It won't matter. Asymptotically, we can say, well, 101 is obtained for 51. Because we can round the half to either 50 or 51. And then from here, what do I get? 102, then 202. 404. All right. How about 52? That's going to give me what? 51 also going to give me who? 102. And then 52 is going to give me 103, 104. 53 is going to give me 105, 106. Then this is going to be 210. This is 212, right? So what are the base cases that I'm going to need if my claim starts at n equal 50? Up to, what's the last base case that I need? 99. Because 99, that I think is his point. You can't get any one of these numbers from the induction hypothesis, right? You have to prove them manually. So 99 will give me 198 and maybe 197. So there's a lot of base cases in there. All right? Completely speaking is going to work that way. In practice, when you get to some inequality, you know that if something happens for, say, 50, it's going to happen for anything bigger than 50 because the arithmetics of those polynomials or exponential works that way. If you need to prove this for, say, 50 to 99, it's easy to see that maybe you just need to prove it for 50 or 51 and then you're done. 50 I pick as an example here. All right. So that's what we have in here. Let me do another one. So this is 2n by 2 plus n. I think we put on the board another one that was T of n is n for n by 2 plus n. I don't know if this was one of the examples listed in the master theorem. How do we expand this one? What's the next step? T of n by 4 plus n by 2 plus n, which is 4t of n by 4 plus, I can write 3n. I'm not sure that's going to be the most easy to guess the pattern with 3n. We can try 3n, or we can try n plus 4 plus n plus, and it's from here. This is 2n, right? How about we expand this again? 4, what do I get in there? 4 p of n by 16 plus n to the
Wouldn't it be by 8?
8. I skip ahead. Plus n by 4.
4, yeah.
Shouldn't it be 16
Miss
times
the
4?
4 up in the top.
I missed a 4 here?
Yeah.
Huh. So that's 16. Is this correct?
Yeah.
16. Very good. So then I get a 16 in the front here. Plus n plus 2n. Or again, I can write as 3n. Let's see what's better. What happens here? I get 64 t of n to the 8, right? Plus, I got n plus 2n plus how many n's are here? 4n. See, I think this would be easier than writing it as 7n, because it's not immediately clear 3, 7, whatever's next, but in this form, I think it's going to be more clear. One more time. 64 times 4t expansion of this, right? It's n by 16 plus n to the 8 plus n plus 2n plus 4n. So that's going to be 64 times 4? 256 t of n by 16 plus, I'm going to try to do n common factor here. I get n plus 1 plus 2 plus 4, and now this 64 times n by 8 is going to be 8n, so it's plus 8 in here. Can we guess the pattern? This is still, the whole thing is still T of n.
Would it be 4K? Yeah, 4 to the K.
4 to the k times T at T of
And with 2 to the K plus n times the summation of I equals 0 to K.
1 maybe? Oh, 0. I see. You're 2 to the 0 here.
Yeah, 0 to K minus 1. 2 to the K.
I.
Or 2 there, yeah.
That summation is just 2 to the k minus 1, isn't it?
Yeah, either way works.
2 to the k up, minus 1 down. Right. But if everybody, before we jump ahead, can we get everybody in here? Where is this coming from, this sum? This sum is this from, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, right? That's 4. Of course, this was k equal 4 here. What will this sum be here? This whole thing was n times 2 to the 0 plus 2 to the 1 plus 2 to the 2, right? For k equal 3. So one of the difficulties here, it's guessing. I know it's very easy when somebody writes it on the board from the notes. Yeah, if without those notes, even me, I would be like lost in here, right? I mean, I'm lost already. You can tell from my right? And somebody that says you nice 1, 2, 4, 8. What's the next one? It's easy to guess it that way. When you write it on scrap paper in an exam, that's fast. It's not that easy to guess these things. So the sum here is the general version of these 4 k steps. So now, what's the last k? How this thing ends? This is the same I had before previous 2 exercises. It's going to end when 2 divided by 2 to the k is 1. But it doesn't have to be 2 to n divided by 2 to the k. It's because I always have n by 2 in the parentheses here. Last k is n divided by 2 to the k is approximately 1, which means k is approximately log base 2 of n. So now if I substitute that k in, I get T of n is 4 to log base 2 of n. I'm replacing this k with my last k times T of course, how did I choose the k? The interior to be 1, right? No surprise, I'm going to get 1 in there. Plus n. Somebody said they know the formula for this. It's a geometric series.
2 to the k.
This is 2 to the k minus 1 down. Right? Do you remember that? 1 plus 2 plus 4 plus 8 plus 2 to the k minus 1 is actually 2 to the k minus 1 divided by 2 minus 1. But 2 minus 1 is 1. So this will be n times 2 to the, now who's this k? K is whatever I'm substituting here, the last k, that's log base 2 n minus 1 like this.
Yeah.
Okay, how much is this? How much is 4 at log base 2 to the n?
So asymptotically equivalent to 2 log 2 to the n.
So that's a little trick that you have to know. 4 at log base 2 to the n. Anytime you see this, you want to write this 4 as 2 at some power. You're going to write this as 2 at log base 2 of 4. By definition, that's going to be 4 times log base 2 of n. And now you want to reverse the 2 logs. So you want to do 2 at log base 2 of n is what? Right? I can swap those logs. So I get 2 at log base 2 n, everything at, how much is log base 2 of 4?
2.
2, so how much is this? Again, every time you see something like this, a power raised at a log, the easiest way to go by is to write the number 4. So let me write it more general, because this is some trick that if you don't know it, it's going to take quite a while to, I don't want to erase this, I want to erase this in here. Every time I have a at log b of n, how do I do this? I do b at what power? Log base b of a at log base b of n. Now I swap the two logs, log base b of n at log base b of a. So now what I got? B at log b of n is n at log b of a. Now, people can remember the formula a log b of n is n log b of a. The formula says you can just swap the a with n. But I never remember those formulas, so I always remember the mechanism to get them right and by expansion. So that's what I got. N's here, n squared. So this is n squared times t of 1 plus, how much is this? N times 2 at log base 2 of n is n minus 1. So in terms of theta, how much is this? This is n squared, this is n squared. So this whole thing is theta of n squared. Is that what we've got from the master theorem? Was it n squared? Okay, so that's what you're going to have to do. We don't have a quiz 4, but if we have a quiz 4, that's what you have to do in quiz 4. So that's going to be now safe for the final exam. Right? Like before, we could do some induction proofs here. I'm going to skip that step. In the algorithms class, you're going to have to prove this by induction. In here, I want to show you a different representation of this expansion. It's the same thing written with a 3. So the people who did those trees are the computer scientists who are not that good at math. Because they didn't like it that way. It's too algebraic, too abstract. What is all this? I can't think about it. So they like to think, the programmers, in terms of the actual recursive calls, right? If an algorithm tries to do something with an array of size n, what is recursion means for that algorithm? This algorithm is going to call itself how many times? Recursively. If this is the running time, whatever this algorithm does, I don't know, finds magic in the arrays, right? How does it do it? It calls itself how many times? 4 times, and each one of the calls, it's for an array of what size? Half. And then once it's done with those calls, you finish 4 calls of a half each. Then it's a linear time to put together the results. So if you think programmatically, look at the stack of calls that the algorithm does before it finishes. What does it do? Well, you start with t of n right here. And you say, I have 4 branches. That's my initial calls. Each of them is t of n by 2. Right? And if those branches finish, right? This is some procedure that's being called, you know, recursively call that algorithm, but not for the array, just half of it. When they finish, look at my recurrence, the combination time is going to, once they finish, add up n, right? So this one here is going to be the combination time. Let me write it here. It's plus n, once those branches are finished. Now what happens in here when the program calls T of n by 2, how does it do that? It's going to call itself 4 times for what size?
T of n by 4.
It's going to be T of n by 4, T of n by 4, T of n by 4, T of n by 4. And when those are done, it's going to add up in here, what? N by 4, right? This is for the combination time for this branch. Now this branch also going to call itself the algorithm a bunch of times, T of n by 4, T of n by 4, T of n by 4, T of n by 4. And this one too. And this one too. This is a way to look at the stack of calls and total load, if you want, total number of operations the CPU has to do. So what it's saying, each one of the branches splits in 4. Each one will take that much time. But I have, how many times I have to add the n by 4 here? 4 times, right? Because each one of these branches, when it finishes the 4 recurrence calls, will spend n by 4 time. Oh, it's n by 2? Sorry. By 2, n by 2, by 2, n by 2. Once I finish the 4 recursive calls to finish this procedure, I have to add an n by 2 times. So I have 4 of these branches. The total will be this. Now, if I am taking one of these, what's going to happen here? I'm going to expand it into 4. This is going to be T of n by 8, T of n by 8, T of n by 8, T of n by 8. I won't have enough space to expand all of them. But the combination time when those are done, it's going to be an n by 4. Now, how many times I'm going to need to do a combination? Right? This is just for this branch, but there's another one for this branch, and so on and so forth. So how many of these n by 4s I'm going to have there? So I can imagine this going down until I get T of 1, which is the same way I'm saying here when this ends. Right? Again, that tree is the same as this, more visually represented as a stack of calls instead of an algebraic addition. And then I have to compute the depth of the tree. So the depth is going to be log base 2 of n, because I know by cutting in half, I'm going to take log 2 steps of n until the tree is done. And then I have to sum up the total combination load. So when I sum up this combination load, I'm going to get the same result like this. I personally don't like this method. I found it that in most cases, it's hard to draw, and it's hard to keep track of everything. I found myself much more easier working with the algebraic version. Yes?
You mentioned quickly at the end there that you just sum up
Those combination loads, yes.
What do you mean by that specifically?
So I have to figure out the formula. This is n, right?
Mm-hmm.
What's going to be the sum here? N plus 2n plus, how much is this? 4n. This is going to be what? N by 8 times 64. So that's going to be the 8n. That's going to be this stuff here. Right? It's the same sum. You can look at some example. These are not very well drawn in the notes here, but in my algorithms notes, I have some trees drawn nicely. Again, for me, if I don't apply the master theorem, if I have other plans, I would rather do this algebraically to see if I guess a pattern. That's the safest guess. Now, if you know the master theorem, the easiest way is to get the answer with master theorem, and then see how you get to that. The one thing that I want to do here is I want to give you a hint for the master theorem. Not the proof, but a way to say, okay, what were these cases are coming from? Anybody remembers what the cases were? What the question was? Why there are three cases? Who compares to who? The three cases because there were two quantities, and depending how they compare, we get three cases, right? What are the two quantities?
C and log of B.
C versus log base B of A. So where is this coming from? How come is, yes?
It's the C is always like adding to the part of A and B. A and B are always multiplying with each other, where C is separate. So you're seeing which one is bigger.
I don't know. Yes.
It's because the left side of it, or the first term of it, is always just going to go down to n log B of A, and the right side is always going to go to n.
Right, so I think he's saying what I was intending to do here as a hint. Can we do this for the general formula? Instead of 4 n by 2 by, what's A here? A is 4, right? B is 2, C is 1. What if we do this, the whole thing, for actually A, B, and C? Right? Let's try. If we do this for A, B, and C, are we actually, let's leave it on the board here and see if we if we get anywhere with it. I don't want to do a full proof. That's again in my algorithm slides, which we'll put them online. But I want to see how this will look like. So say T of n is A T of n by B plus n to the C. I'm going to do the same thing I did for 4, 2, and 1, just in the general case. So if I expand it again, what do I get? A T of n by B expanded will be who? Well, if you take a look in here, this was for A equals 4, B equals 2, C equals 1. What is this? A T of
Number 2.
n
2B.
B squared. Because it's the n by B divided by another B, right? This is n by B divided by B sort of thing. Because I'm applying it for n by B, plus what's the still inside the parentheses? I'm applying it for n by B, so this orange here is n by B to the C. Is that right? Or not? Hands up who's following me. Must be right. Everybody raise their hands up. So what happened here? I just expanded this T of n by B, just this part, without the A. A is in the front, n by C is here. T of n by B, n by B is the orange now, so T of n by B is A times T of the orange divided by B, plus the orange at power C. My orange being n by B. Right? So let's write this nice. What is it? A squared T of n by B squared plus, I think it's useful to leave this n by C in place to recognize the pattern later. N by C, what's the next one? What's this? Like that? Okay, so who are we going to expand now? A squared, it's A squared. We're going to take this and expand it here, right? So my orange is n by B squared now. What do I get? I get A T of B cubed, right? Because it's the orange divided by B. The orange being n by B squared. So divided by another B is n by B cubed. plus what's inside this parenthesis when I do the expansion? N over b squared, add power, c, plus I still have the remaining thing, n to the c, a, n to the b, at c. So what's going to happen here? A at 3, t of n by b to the 3. This looks nice, looks like a pattern 1, 2, 3, right? That's easy to recognize. Let's see what happens with these other guys. Who is this? This is n at c plus a n by b at c. That's what I've got here. And this other one will be a squared n by b squared at c, right? Should we do another step, or you guys are ready to guess a pattern? Huh? You ready to guess a pattern?
No, another step.
Another step.
2 more steps.
Okay, one more step. This is a cubed times what? A t of n by b to the 4th plus n by b cubed to the c plus n to the c plus a n by b to the c plus a squared n by b squared to the c. Now this is going to be a to the 4th, b to the 4th, right? Plus, let's try to do a grouping at least, right, in here. Is n to the c common to everybody? Can I just do a common factor n to the c? N to the c, then what's the sum? This one is 1. The next one is, it looks to me like it's so okay, it's the first one is a, what is it? A divided by b to the c, right? The next one is a square divided by, well, we miss a term here. We need to have this one too. A cubed n times b cubed to the c, right? This one here. So I'm going to get a to the bc squared, right? Maybe it's like that. A to the bc squared. Is that correct? Would that be this one here? And the next one will be a divided by bc cubed. Now can we get the pattern? After k steps. What is this? We're missing the a here. A to the 4th. So it's going to be a to the k t of n divided by b to the k plus n to the c. That summation, right? Let's say sum from I equals 0 to k minus 1. Is it k minus 1? This is 4 in here, k equals 4. And I got it to 3. This is k equals 3, and I got it to 2. Right? So it's k minus 1. Of, this is a geometric progression, right? Is a to b to the c at power I. Because for I equals 0, I get a 1. Hands up, who's with me? So now you can see, by doing the same exact thing I've done before, what's the last k in here? I need roughly, where does it end? I need n divided by b to the k to be roughly 1, which means k has to be roughly log base b to n, right? Because that's where it gets to 1. So now if I replace k in there, I get t of n. Well, actually, somebody, can we apply a formula here, just the same we did before?
Yeah.
It's a geometric series with this weird r, right? Let's say r equal a divided by b to the c. this would be r to the k minus 1 divided by r minus 1 if r is not 1, right? I can't really apply the formula when r is 1. So that r1 I think is one of the cases of master theorem. I have to take that case separately because this formula doesn't work when this r is 1. So right there I have a case that I have to do separately. So what is r equal 1 case? A divided by b to the c equals 1, right? So what does that mean? C must be who?
One case P of n.
What case was that? 2. Case 2. So case 2 I have to do it separately because I can't apply this formula in here. Okay, so r to the k minus 1 divided by r minus 1. This is going to be a by b to the c at k minus 1 divided by a by b to the c minus 1. So now I get T of n is a at k, that's a at log base b of n, because I'm replacing the k in there. T of 1, that's how I design my case to get in 1 inside, plus n to the c times this thing. A divided by b to the c minus 1 is in here. And this is a divides by b to the c at the power k. K is log base b of n minus 1. And that's not a complete proof, but this is what I want to stop. The people who are interested can crank this formula down to get the other 2 cases of master theorem. One case, we already have it separate, is the case that we couldn't apply the formula. Now there's 2 more cases. It has to do with what term dominates, right? Between 2 functions, you clearly have 2 functions. The story is going to go like this. If this is the dominating term, bigger term, the answer is going to be a at log base b of n, but we know we can swap those, right? This is who?
N log b of n.
N at log base b of a. So that's going to be one of the cases. If this function is bigger, meaning this n to the c times whatever comes here, then this is going to be the dominating in the theta. I'm going to get n to the c. You have to play this out. Now in this particular case, in case 2, which I couldn't apply the formula for, what is the answer? Because this doesn't work. It only works for r not 1. So how do I do this? I'll have to do it, in this case, it will be a at log base b n, right? This part, t of 1, plus, in here it's n to the c, right? I have to do that sum manually. How much is this sum? Everyone is 1 in this sum, right? Because a divided by b to the c is 1. So it's 1, 1, 1, 1. How many times? I think k times. Because it's from 0 to k minus 1. So that's, how much is k? It's sum of 1 from I equals 0 to k is log base b of n, right? So this I think is a at log base b of n, which is, we said we can reverse those things, plus this is n to the c times log of b of n, right? But c is log base b of a, so this is n at log base b of a plus n at log base b of a times log of n. So you can see in this case, this one dominates, so that's the theta. That's the theta function. Because this clearly is bigger than that. Between 2 functions, the bigger one. Now, this is completely not required. I'm not even going to mention it again till the end of the term. But I want you to have an idea to see that the master theorem is really doing a recurrence like the other 3 or 4 we did, in a more general case. It's nothing special about master theorem, just be careful with A, B, and C, which are harder to do in the general case than it's 4, 2, and 1, because those are nice constants to work. Just in time. I guess we don't have attendance today. Quiz tomorrow and Thursday.
I need to know what that substitution stuff is. What numbers do you?
I don't know. You have to ask. I know you can get the
Make it so you can't get it wrong.
It's done for the whole class.
So that way, so you memorize that and you know the answer. So if you didn't take it off, you know you're wrong. You're not allowed to use it.
Yeah, master theorem doesn't exist in this class.
You can get the 2.
Oh, did you decide to talk?
I saw you.